So in this video, we're going to talk about an alternative method for finding volumes of solids of revolution, which is typically referred to as the shell method, or volumes by cylindrical shells. Okay, so by way of an example to motivate this method, let's suppose we wanted to find the volume of the solid obtained by rotating the region bounded by this y equals x times x minus 1 squared and the x-axis about the y-axis in this case. All right. So far all we've talked about is the disk method. If we were going to do, or the washer method, if we were going to use the disk or the washer method, then we would need to slice perpendicular to the axis of rotation. In this case, that axis of rotation is the y-axis. So we would have to slice this way. Okay. So here is what a particular representative slice in the region would look like. We would have a rectangle that goes here from a left bounding curve to a right bounding curve. Okay. Ordinarily, we'd say, okay, no sweat, I'll find the left bounding curve and the right bounding curve. Well, look at this function, though. This function is x times x minus 1 squared. Remember, if we're going to slice perpendicularly to the y-axis, that forces us to integrate with respect to the y-axis, which means that absolutely every single thing has to be in terms of y, not in terms of x. That would mean that I would need to solve this cubic equation for x. Now, unless you've had a really advanced algebra class, you can't solve for x here, okay? So it's very difficult to figure out what the left curve and the right curve here is because this is a hard equation to solve for x. And in other examples, you'll have things that will just be flat out impossible to solve for one of the variables, and you'll be forced to integrate with respect to the variable that you're given. Okay, so we might as well treat it like that in this case. We are forced to integrate with respect to x because for all intents and purposes, solving for x here is going to be very difficult. All right, so if we want to integrate with respect to x, that means we're going to start slicing this way, perpendicular to the x-axis. All right, so in this case, when we do this, we're going to get what's referred to as a shell when we rotate rather than a washer. And so this is what's going to be referred to as the shell method. All right, so let's show you what that looks like using Geogebra again. All right, so here's our curve, x times x minus 1 squared, and this is our region that we're interested in. All right, so if I look at the volume of the solid revolution, so we're rotating around the y-axis, so the green axis here is the y-axis. If we rotate around, here's what our surface looks like. Okay? I'll give you a little bit of an idea of what the surface looks like. Okay, so again, we're going to slice up the x-axis because we want to integrate with respect to x. Okay, so let me get this out here a little bit so you can actually see what a slice would look like. All right. So here would be what a rectangle would look like in the xy plane here. And then if we rotate that around, you get what's commonly referred to as a shell. Let me get rid of the surface so that you can see what I'm talking about. So we get a cylindrical shell. So here's a little cylinder. Okay. As we move this around, you see the cylinder gets bigger or smaller depending on the height of not only the height of the surface at that point, but also how far away we are from our axis of rotation, but we get a cylinder. Think of the cylinder as a paper towel, the inside of a paper towel tube, or the outside of a Pringles can. That's the idea of what we have for a shell. All right. So again, like we do in anything else, our whole goal here is to try to figure out what the volume of one of these shells is, add them all up as you go through the entire region, recognize that you have a Riemann sum, take a limit, you get a definite integral. And that's going to be the theme of lots of different applications that we do in this course. All right, so let's first figure out how we find the volume of a cylindrical shell. So let's imagine that we slice that shell along its height. Go back over to the picture of the graph right here. What I mean here is that imagine that I've sliced it this way along its height. And then we're just going to take it and roll it flat. So again, if you think about a paper towel tube, imagine that you're just taking that paper towel tube, take a pair of scissors, go right up that paper towel tube, and then lay it flat like it was a sheet of paper. Okay. All right. So here is our our cylindrical shell. Here is our height of the shell. Here is our radius of the shell. Here is our thickness of the shell, and so that's going to be our delta x. That's going to be the width of our rectangle, of course. We're going to slice it right along this height and roll it out. All right. When we do that, we see a rectangle. Now this height, when we cut this and roll it flat, this height doesn't change. However, this side is the circumference of this circle. We know that circumference is 2 pi r. We didn't change the thickness either, so that's still delta x. So this little thickness here is delta x. This whole side would be h. That's corresponding to this height. This side now is corresponding to the circumference all the way around that circle. But now this is a little rectangular box, essentially. Right? Maybe I should say a thin rectangular box. We can figure out its volume. So if r is the radius of the shell and h is the height of the shell, then the volume of that shell is going to be 2 pi r, the circumference, times the height, times the thickness. You might recognize 2 pi rh as the lateral surface area of a cylinder, which is exactly what this is, right? That's the surface area of that cylinder. All right, so how are we going to do this now in general for a general function when we're doing this shell method? Yeah, we're going to do it just like we did for washers and discs. We're going to slice up our interval into n subintervals and pick a sample point. All right, so here, sliced it up in n intervals. Here's one representative interval. Here's one rectangle. If we take this rectangle and rotate it around the y-axis, we get one of those shells. So I need the radius of that shell and the height of that shell. Okay. Well, the height's easy, relatively speaking. The height of the shell is the same thing as the height of the rectangle. So the height is going to be f of x by star, just like it is when we've done areas, and just like it was when we did radii when we were doing the disk method to start with. All right. What we need to know is the radius of the shell. Well, remember, we're taking this rectangle, rotating it around the y-axis. So the distance from the y-axis to this x-coordinate is the radius. So that distance is just x by star in this case. So the radius is x of I star. The height is f of x of I star. So the volume then, using that formula we generated or developed in the previous slide, it's 2 pi times the radius times the height times the thickness of the shell. And we recognize that if we did a summation out in front of this, we would have a Riemann sum, right? Because it's sum of function of x of I star times delta x. So when we take a limit, we get an integral. And so this is our integral that we get when we're doing the shell method. It's 2 pi integral from a to b x f of x dx. All right, so let's go back to the example. Our function was x times x minus 1 quantity squared. So we're just plugging that into the formula now. Distribute through everything out, anti-differentiate, plug in your endpoints. So in this case, we get the volume is pi over 15. Let's do another example here. Let's say we want to do the volume of the solid obtained by rotating this region. That's y equals root x. That's this line, this curve, I mean. X equals 0, of course that's the y-axis, and y equals 2, and we're going to rotate it this way. Now we've seen how to do this with the washer method, and we'll verify that the washer method gives us the same as the shell method here, but let's do this with shells. I'll do it with washers first, since it's what I have in the slides. We can do this with the washer method from what we did previously. So washer method, again, we would slice perpendicularly to the axis of rotation. That means we're slicing a vertical slice, perpendicular to the x-axis. Right? Now again, as soon as we make that choice, we are choosing that we are going to integrate with respect to x, period. Okay? When you make the choice of which axis to integrate with respect to, or which way you slice, that tells you what axis you're going to integrate with respect to, which tells you what everything has to be in terms of. Integrate with respect to x, absolutely everything has to be in terms of x. All right, when we do this rotation now, we get a washer in this case. The large radius is 2, because we're going to go from the x-axis up to the line y equals 2. The small radius is root x, because we're going to go from the x-axis up to the curve y equals x. Washer method says we do pi times the integral over the entire region. In this case, these are x values run from 0 to 4. Big radius squared minus little radius squared. Makes a fairly straightforward function to anti-differentiate, and plugging in the endpoints then gives us 8 pi. So we did that in the previous section, talking about how to do volumes by slicing, with washers in that case. But let's see how shells compares. If we're going to use shells, this rectangle should be horizontal, not vertical. So this is the picture is not correct. Imagine this is gone, and we have a rectangle that's going left to right here, a horizontal rectangle. All right, so the reason why we need a horizontal rectangle again is because we want to create a shell. We need to be parallel to our axis of rotation. This would be perpendicular. So we would go parallel to our axis of rotation and go this way around the x-axis. Okay. So the radius then, well, as soon as we, again, like I mentioned in the previous slide, as soon as we would slice it this direction, slice it perpendicular to the y-axis, we are forcing ourselves to integrate with respect to y. Means absolutely everything has to be in terms of y. Again, now we're parallel to our axis of rotation, so it's the shell method that we're using. So we need a radius and a height. The radius is always going to be from whatever x or y coordinate we're talking about. In this case, it's a y coordinate. From y to the axis of rotation. So that's just y. The height is the height of the rectangle. Again, in terms of y, this would be y squared. We started with y equals root x. You square both sides, you get x equals y squared. So now plugging into the formula that we developed, 2 pi times the radius times the height. Notice in here we have the interval from 0 to 2 now, because again these have to be y values, not x values. Our y's go from 0 to 2. Simplify, anti-differentiate, and get the final answer here when we plug in our endpoints, which was the same answer as we got on the previous slide. So in this case, we could have used either the shell method or the washer method, whichever one, but there will be instances where you have to use one method or the other. So we'll talk about how you make those decisions in a subsequent video.